In this short video, we will go over some problems in terms of insertion sort, selection sort, and merge sort. So let's take a look at the first problem. We are trying to solve this problem of counting compares. We are given a very special type of an array where we have n b's and n a's. So the question is asking how many compares does it take for the insertion sort to sort the array as a function of n. So in order to understand how the insertion sort works, insertion sort starts by doing this. It'll start from it assumes that the first one is already sorted. And then the second one, it will try to compare until it finds the right place, insert it, and shift the elements to the right. So in this case, we find out that the b is already in the right place, and therefore you don't do any sorting. So this array is now sorted. You look at the next b, you do the same thing. You just do one compare, and you realize it's in the right place. So if you think in terms of that, you have a sorted array of n b's, and it only takes n minus 1 comparisons. 1, 2, 3. Each one requires 1, and there are n minus 1 comparisons you do to know that this portion of the array is already sorted. In other words, insertion sort is one of the best sorting algorithms, and the array is already sorted. Now let's take a look at A. Now, in order for A to be inserted into the right place, it'll have to be compared to B, and this B, and this B, and it'll have to be compared all the way to the end. So in other words, it will do n comparisons to insert A to the right place. So it will be doing n comparisons to insert A into the beginning of the array. And then if you take the next A, it'll do the same thing. It'll go, this A will go all the way here. So it'll require n comparisons to insert that second A into the right place. So now for each of these A's, we have n comparisons, and we have n A's we need to insert. So we will have to do n times n comparisons. In other words, we come up with n squared plus n minus 1, which is in tilde notation is n squared. So the answer to that question is n squared. Now let's take a look at the selection sort idea with the same array. Once again, we got n b's followed by n a's. So the selection sort idea is that you always find the minimum among all of these things. In a regular selection sort, you go through the array, find the minimum. That requires n minus 1 comparisons for an array of size n to do. Once you do that, you insert it, you swap that element with the minimum, and you continue. But next time, so you would, in the first iteration, you would be doing n minus 1 comparisons. But now that the minimum is already in the right place, we don't have to worry about that. We just have to worry about an array of size n minus 1. Now, to find the minimum of an array of size n minus 1 requires n minus 2 comparisons. And if you continue that argument, you would finally get to 1. And what we know is this is a sum, which is 1/2 n minus 1. In other words, we know that this is tilde 1/2 n squared. Now, in this case, that's for an array of size n. But we have an array of size 2n, and so all we need to do is replace n by 2n, and then we get the answer 2n squared. So that is the answer to that question. Now let's take a look at a modification of the two-way merge sort called the three-way merge sort. So in the three-way merge sort, we take 3 subarrays of size n over 3, we merge them into one sorted array of size n. So how would we go about doing this? Let's think about two examples. Let's suppose, well, first algorithm would be to consider all three sorted arrays of size n over 3, compare elements from each array. So we compare one from here, one from here, one from here. So there are two comparisons. You need to find the minimum of these three elements. Once you find the minimum, you would merge them into the one subarray of size n. So it required two comparisons to do that. Once you do one time, let's suppose that was the minimum, then you consider this, this, and this again, and find the second one. So you do another two comparisons to find the second element. Since you have to do n of those things, and each one requires two, you would be doing 2n comparisons to merge all three arrays into one subarray. An alternative approach is to consider only two arrays at a time. We consider two subarrays of size n over 3, and we merge them into one subarray of size 2n over 3. So in this case, you would consider the two elements, find the minimum, and place it here. So you only required one comparison to get one element into that. Then, assuming this was the minimum, we consider this and this and get the second element. So for each of these 2n over 3 elements requires one comparison, and therefore it requires a total of 2n over 3 comparisons. Once we do that, we must merge that subarray with the remaining subarray of size n over 3. So in that case, we are going to merge these two into one subarray of size n. So again, what we do is to compare an element here and the element here and merge it into that. That requires one comparison. Since each of these things require one comparison each, and you have to create an array of size n, you would require a total of n comparisons. Considering that, since we did 2n over 3 before, now we did n again, you would require 2n over 3 plus n comparisons according to that algorithm. So that would be 5n over 3 comparisons. So in the previous approach, we had to do 2n comparisons. In the new approach, we have to do 5n over 3. Among the two, this seems better. 5n over 3 is smaller than 2n. So you can assume that in the merge step, when you do 3 arrays of size n over 3, the number of merges you have to do is Cn, where C is either 2 or 5 over 3. Now, we want to argue that the number of compares to an array of size n using three-way merge sort is still linear arithmetic. The idea is that when you think of merge sort, we divide the array into 2, but in this case we divide the array into 3. And then we divide the array into 3 again. So if you think about the height of this 3, that would be log base 3 of n, approximately. And each step of this idea would require Cn comparisons, where C is either 2 or 5 over 3. So still we can argue that our three-way merge sort is also linear arithmetic. It's still n log n from the order of growth perspective, n log n, but the constant is either 2 or 5 over 3. The next one asks whether we would choose three-way or two-way merge sort. Now, the way we think about merge sort is that merge sort, all the work is done at the merge level. So in a two-way merge sort, the C is 1, as we saw in the lectures. In a three-way merge sort, the C would be either 2 or 5 or 3, depending on which algorithm you choose. And so if you have a choice, you would still go with the two-way merge sort. So two-way merge sort is perhaps a better merge sort, although they both have the same order of growth. From a runtime perspective, having a smaller c is a better idea.